So here's part B of number 5 from the 2014 AB Calc exam. And in part B it says explain why there must be a value C between -1 and 1 such that f double prime of C equals 0. Well, anytime you have a situation like this, if you're asked to explain why or prove why a function has to equal a certain number on a certain interval or a derivative has to equal a certain number on a certain interval, you should hopefully key in on one of two theorems, either the intermediate value theorem or the mean value theorem. Now, if you want to say that a function that you know values of has to equal a certain number, that would be the intermediate value theorem. But if you want to say something about a derivative equaling a certain value on a certain interval, mean value theorem is going to probably do the trick for that, because what the mean value theorem says, and I'm going to use a different function than you're probably used to expressing this with. I'm going to use the function g. I'm going to say that g prime of C would equal a certain number, and that number would be found by taking the slope of the secant line connecting A to B on that curve. So this says the average rate of change of a function is going to equal the instantaneous rate of change on a function as long as that function is continuous and differentiable on any interval that you choose to look at it on. So here it asks us to say that a derivative has to equal a certain value. So I'm going to try to see if we can go with the mean value theorem here. Now, if you think about what we're capable of doing, if you're trying to apply the mean value theorem and you want to have an f double prime of C be generated, if I just swap out the g prime for f double prime in the conclusion of the mean value theorem, it can look like this. Now, I don't have primes in this numerator because this is the derivative of what we see in this numerator. So if this is the derivative of what I'm going to see in the numerator that I'm about to put right here, I need to hopefully realize that that derivative is going to be f prime. So we don't normally do this, so this is a little bit of a weird situation that we're trying to apply the mean value theorem to, but this is an equivalent conclusion to what we said back here, because we have the derivative of f prime at C equaling the average rate of change of f prime on the interval from A up to B. So the only thing that we have to double check before we go ahead and try to apply this is whether or not f prime is continuous and differentiable. So is f prime continuous and differentiable? Because those are the two things that have to happen in order for you to be able to use the mean value theorem. So if you read this problem statement, it says that f is a twice differentiable function. What that means is that the first derivative always exists everywhere, meaning f prime is continuous. The first derivative is never undefined. And then the second derivative always exists everywhere. And if the second derivative always exists everywhere, then f prime is differentiable because f double prime always exists, and that would be the derivative of f prime. So yes, we can use the mean value theorem, and we want to use the mean value theorem applied to f prime of x on the interval from -1 up to 1. So I'm going to take the right side of this equation right here, and I'm going to put 1 in place of b, and I'm going to put -1 in place of a. And if you simplify this, the denominator is going to be a 2. And in the numerator, if we go ahead and go to our table, we know that f prime of 1 is 0. So f prime of 1 is 0, and then minus f prime of -1. So here's the row for f prime. There's the column for when x is -1. That's another 0. So we have 0 over 2. So by the mean value theorem, since f prime is continuous and differentiable because of the fact that f is twice differentiable, the mean value theorem guarantees that for some c between -1 and 1, f double prime of C will equal 0. You'd want to write out that statement that I just made on your page in order to receive full credit for the explanation.